All right, so for our exponential functions here, the warm-up question is trying to explain kind of how the idea of exponential functions work compared to just a regular linear function. So there's two plans here. It says your soccer team wants to practice a drill for a certain amount of time each day. So the one coach or the one plan says 5 minutes today and then 1 minute more each day than the previous day. And then plan 2 says we're going to start with 1 minute today and then twice as much time as the previous day. So initially the first plan, we're going to kind of look at this, plan 1 here. So the first day we would do, so kind of like just setting this up. So in day 1, 2, we're going to go up to 8 days, 3, 4, 5, 6, 7, 8. And then we'll do plan 2. So plan 1, the first day we're doing 5 minutes of the drill. So it says your soccer team, so maybe it's like dribbling or something that you're shooting on goal or something like that. And then 1 more minute each day. So the next day we would do 6, 7, 8. So by the 8th day we're doing 12 minutes of that drill. That seems, I think, reasonable. Plan 2 though, if we start doing this, so the first day sounds like 1 minute, no big deal. Maybe like you're like, I'm gonna do a plank for a minute today. But tomorrow I'm gonna double it. So I'm gonna do twice as much. So I'm gonna do 2. But the next day I'm gonna double that. So then I'm gonna do 4. I'm gonna double that and do 8. Double it, 16. So by the 8th day, we're doing 2 hours of whatever that drill was that we only did for a minute the first day, 128 minutes. So it asks you guys, are these plans reasonable? And it kind of depends how much time we're talking about. If we're saying for the whole month, probably not. By the end of the month, we'd be doing probably more time than there is in a day. So plan 2 is what we consider exponential growth. It starts growing pretty slowly and then all of a sudden it like explodes and we're like, what just happened here? I don't know if you guys have ever had like fruit flies in your kitchen. All of a sudden you like see one fruit fly and then like the next day if you don't take care of whatever it is that they're eating, there's a whole bunch of them. And it's because they reproduce so quickly. And that's an idea of exponential growth. So in terms of these plans, the second plan probably is not reasonable because if you could only do for a minute, like again, let's say it's a plank or something, to hold a plank for 2 hours probably seems a little crazy by the 8th day. Speaking of weird plans, so I've mentioned before, I run, I like long distance running, so like yesterday after school I went and ran 7 miles outside, and that's a pretty typical run for me. But I have a friend right now, so anytime I feel like I'm doing a lot, I think about her. This month, she's running the month is what she's calling it. So every day, so today's the 21st day of the month, so today she's running 21 miles. But she's been doing that all month. So the first day she only ran 1 mile, but now she's up to 21. So like this week alone, I think she said it's like 70 miles or something. It's crazy. So like, so anytime I'm like, I'm doing a lot, then I think about her. So by the last day of the month, she'll be running like 28 miles a day, which is pretty crazy, but things we can do if we push ourselves. And she does break up her run. So like yesterday, I know she ran like a little bit on the treadmill in the morning. She did like a lunch run, and then she finished the day running like with her dogs or something. I don't know how she has all this time in the day, but that's so if you think you're working hard, then you think about somebody who's working a little harder, maybe a little crazier. Okay. So the idea of exponential growth is something that exists in real life. So you might say, like, when does that ever happen? It happens again in science. It happens in economics. There's all sorts of places that this can be the case. So we've talked about 2 different types of equations. We have both linear and exponential. So linear is what we've been talking about this whole year. So linear is y equals mx plus b. So if you were to describe to someone who knows nothing about graphs, So maybe your younger sibling, and they say, what's y equals mx plus b? What would you tell them about the way that graph would look? Yeah.
It goes up and down, side to side.
Up and down, side to side, but it's a straight line, right? So it's straight. So it has that straight line to it. And what it's doing is every single time we move from a point to a point, like when we do our rise over our run or our slope, like when we go up 3 and over 1, or like for instance, they added 1 in plan 1. So they started at 5 and then they went up 1 over 1 in terms of our graph. Guys, make sure we're paying attention. We're changing every day, we're going up 1 and then over 1. So we're either adding or subtracting a number more and more each day. So we increase or decrease. So our linear functions typically would look like this. And we increase or decrease them by addition or subtraction. So we're going up by the same amount each time, or we're going down by the same amount each time. I'm adding 3 more each time, or I'm subtracting 2 more each time. It changes in the same way over and over again. Now our exponential equation we're going to talk about, the way this is going to look, we still use y and x, but instead of an m and b, we're going to use an a and a b. So this is typically what an exponential equation can look like. It has some variations it can have, but for the most part. But the way this graph is going to look, it's going to kind of look like almost like a kind of a strange looking J. So this would be exponential growth. So this would be an example of, again, like, so if we didn't hunt deer in our area, eventually, like, the deer population would grow kind of exponentially because they don't have predators in our area unless we're hunting them. There's other populations that will happen if they don't do something about it. Whereas decay, and there's actually like things called like half-life, so like if you bury something in the ground, it starts breaking down pretty quickly, but then eventually it gets like, it kind of levels off, like it keeps getting smaller and smaller, but then it never quite goes away completely. So exponential decay would be going downhill. So it has a curve to it. So it's a curve versus a straight line. And this one increases or decreases. With repeated multiplication or division. So a lot of our graphs today are going to look a lot like that, but again, it's not going to be as detailed as a linear graph. Like it's not going to be as perfect. I'm not going to be as picky about, oh, you changed the slope part of the way through. We get to kind of have a little more variance to that. All right, so let me show you guys another couple vocabulary words here. So the first word is the domain. And this is a word you're going to use throughout the rest of your high school math career. I think we talked about it a little bit earlier in the year. This is the possible x values. Now we're choosing x values for our graph. Make sure you're taking notes with us, please. The possible x values we can choose, it's for the exponent, so the exponent really can be anything. So we're gonna say that x can be all real numbers. And this will be the case for every one of our problems today. What that means is we can choose anything. Now, there's gonna be points that are gonna be better than others. I wouldn't choose 500 for my x, because that's gonna be the exponent. And 500 as an exponent means I'm multiplying something 500 times. Probably not gonna pick very large numbers like that. So I'm usually gonna stay in between like -2 and +2, somewhere around there. Sometimes I'll alter things a little bit, but really anything does work. Now the range is gonna depend on our graph. So this is the possible y values. And we're gonna use the graph to help us see this. And so we'll talk about that. So the range is a little more confusing to kind of figure out here. So again, what we're gonna do is we're gonna graph some of these. I don't know how many we'll actually do. We'll kind of hopefully at least 3 of them here, and then we'll do that word problem in the back too. But. So this first problem, it says graph y equals 2 to the x power. So again, for my x value, I can choose whatever I want, but I'm going to try to be smart about this. So I'm going to pick -2, -1, 0, 1, 2 right now. I used to have like a video to explain exponential decay and then or growth, and then YouTube took it off, so it's gone. Not because there was anything wrong with it, it must just, I don't know, the count was disabled or something. So now for our y, what we're doing is we're putting our x in using what we know about variables. Now, you might want to start someplace else, it's up to you, but if we do 2 to the -2 power, now in this case, I'm okay with you doing this on your calculator. Just in case you're not super comfortable with this. Guys, make sure we're following along, taking notes, please. So 2 to the -2 is really like 1 over 2 to the second. So 1 over 4, but if you put that in your calculator, you should get 0.25. And if you don't know how to put this into your calculator, please ask. So 2 to the -2 power, and your calculator, a lot of you guys use this little caret button. If you don't have the caret button, you might have something else. Okay, so if you do 2, type in 2 first, and then yours looks different. Yeah, maybe. Yeah, I can't see it. That's really weird. There's 2 to the second. Anybody else have trouble finding on their calculator? Evie's calculator here is a special one. There's a reason it was on sale. All right, so 0.25, again, knowing how to put that in your calculator. So then 2 to the -1 power is going to be 1/2 or 0.5. So really knowing how to put these into our calculator, did you try it? Did you get to work? So 2 to the -2. Okay, then you have to ask. That's why I have you guys doing this. So 2, and then we have to raise it to a power. I do not see it. I would suggest grabbing one of mine. Figure it out in yours. You guys all find it? Yeah. So 2 to the, okay, yeah, no, that's okay. You can put negatives in. Dean, are you with us? Gotta be awake. Okay, you guys all find it in your calculator? Yeah, okay. Then 2 to the 0, that one maybe you shouldn't have to do it all. What's 2 to the 0? Find it in yours. 4th or 0.25. 2 to the 0, we should just get 1. 2 to the first, we should just get 2. 2 to the second, we're getting 4. If you're not understanding how I'm getting those numbers, please, please ask. Because this is a pretty straightforward, dare I say, simple example, and we want to make sure we have this done correctly. Now notice the graphs don't have a normal XY axis. The reason for that is because I don't need part of the axis, I'm guessing. So I'm going to actually put the axis down the center, and then it kind of low over here. The reason I'm doing that is because I know I have to go to -2, and then 0.25 is going to be really low, like, I mean, it's almost like at 0, so really small down there. -1 and then a half, 0 and 1, 1 and 2, 2 and 4. And like if you're kind of curious, because there's a whole lot of graph ahead of this, I'm going to do 3. So 2 to the 3rd power is going to be 8. So sometimes I'll do more points just out of curiosity. And so again, the shape of our graph should be kind of this J shape. Now, if you think about this problem, we want to think about what the y could be. So in this graph, what we're looking at here is, if you guys notice, it keeps getting smaller. It keeps going half and half and half, smaller and smaller and smaller. But it's never going to go negative. 2 to some power is never going to be a negative number. So what we're going to say the domain is x can be anything. But y we're going to say is going to be greater than 0. So that's the range, sorry. Domain, x is anything. Whereas the range, we're going to say y is greater than 0. And that's kind of based off of what I'm seeing from our graph here. And we'll practice that a little bit more to make sense of it. But this is really all we're doing today, is we're picking values, substituting them in, and then try to draw the graph that goes with it. So our next one's a little bit trickier, and again, I would really suggest making sure you guys grab a calculator and practice this with us, if you haven't already. So we have our x and our y, and again, I'm going to use those same x's and y's. So I'm going to do -2, -1, 0, 1, 2. And sometimes I leave a little bit of space in case I need to go smaller or bigger. Now if I do 1/2 to the -2 power, what that actually does is both of these become a negative exponent. So we actually would flip it over. So it's actually going to become 4. But you don't have to do it by hand. You can put that in your calculator. So in your calculator, you should be able to type in 1/2 to the -2 power. If you don't know how to do that, you probably need parentheses. So I put in parentheses, 1/2 to the -2 power. Grab a calculator. You guys feel free to grab a calculator. You guys have to be practicing this. Everyone get that to work? 1/2 to the -1 power is going to be 2. What you're going to actually notice in a second, I think hopefully you'll see it, is that this table is actually going to be flipped with the last one. Yeah, it's kind of fussy with that. So. And then an arrow over, yeah. One more key. Another one. There, now we close that and then raise it to the power. Yeah. 1/2 to the first power is going to be 0.5. So this graph is actually the completely flipped version of the last one. So this one is kind of the ideal of exponential decay. So this graph is getting smaller really fast. So again, if I was to check like -3, I would find out that's 8. So this graph just does the opposite. It starts big and then gets smaller and smaller and smaller and kind of levels off. So it never quite goes away. So again, the domain for this, the possible x's, I could have chose anything. Whereas the range, again, that's the y values. Notice on the graph, I didn't make a y, I didn't put any negative values in my y, because my graph is never going to go below that y-axis. So we say y is just greater than 0 again. All right. A lot of the ones we're going to do today, I'm going to let you guys know it's either going to be y is greater than or less than 0 for our range, just kind of getting used to seeing that. Let's do one more here. This one's a little bit more complicated because it asks us to do 2 things, and then we actually might wait on the word problem. I didn't put any of those in our homework for tonight. So let's do this one. I'm going to actually move my graph up so I can, I think I'm going to. This one's a little bit more complicated. So again, we want to be able to practice this using our calculators. So again, I'm going to pick the same x values I've been picking. But I leave a little space above and below depending on what I want to like check on what's going on here. Now this is a little bit different. When I put this into my calculator, I have to be careful. So I'm not doing, this is not the same thing as 6 to the x power. So don't change that and say, well, 2 times 3 is 6. Why isn't she just doing that to the x power? That is not what we're doing here. So what we're doing instead is we're raising 3 to that power, and then we're multiplying it by 2. So when I go to do this, I do 2 times 3 to the -2. You can put that in your calculator exactly how it is, or if you want to think about what's happening here, it's really 2 over 3 to the second, which is 2 over 9. And 2 over 9 is going to be 0.2 repeating. So when you do 2 times 3 to the -2 power, it's going to be 0.2 repeating. When you do 2 times 3 to the -1 power, this is going to be 0.6 repeating, so I'm going to call it like 0.67. And again, putting that in your calculator and making sure you're getting that. Let me know if you're not getting that to work. Now careful, 2 times 3 to the 0 power is a tricky one. We do 3 to the 0 is 1, but then we have to multiply it by 2. So we're actually going to get 2 for that one. Two times 3 to the first, should get 6. 2 times 3 to the second, we should get 18, I believe. So this is one that starts really, really small and then gets really, really big. Right? I think it, because it's 2 to the, or 3 to the second is 9 times 2 is 18. Yeah. So this again, really small, it starts off, then it starts getting bigger, and then it gets really big, really fast. So I'm already off my graph by the second point. And you might say, well, that graph looks a lot like all the other ones we've done. And they do, but again, that table of values is essential when we're doing this. And again, in this case, our x can be anything. And again, our y is always going to be greater than 0 in this case. So, I opted, I don't know if I printed, yeah, I have book pages there. I decided to do a worksheet instead, just because there's all this graph paper. So I have graphs for us. And we'll talk about that word problem next